Let's take a look at a vibrating system which has a forcing function that's acting on it in the form of a sinusoidal input. We could get a force like this that might be generated from an imbalance inside of the system. Here I'm modeling that as a rotator here that's spinning with some beta, and it has an offset weight, so it's imbalanced. And that imbalance will impart an oscillatory input to the system. And our forcing function will act sinusoidally based on the cyclic motion of this imbalance in here over some frequency which we'll call beta, which will be our forcing frequency. And let's see what effect this has on our system's resonance patterns. Our free body diagram, we would still have our minus kx from the spring here, and this is undamped. And if we go to Newton's law then, we have minus kx plus p sine of beta t is equal to mx double dot. And if we divide through by m, and then rearrange this, we'll get x double dot plus k on mx is equal to p on m sine of beta t, where we recognize our normal harmonic motion differential equation. In fact, here is our omega squared term. And now it's non-homogeneous because we have an extra forcing function on this side. And from differential equations, we know the solution to this will be some general solution G, which will consist of a homogeneous portion plus a particular portion, because we can model this as plus 0 on this side. So this function has to generate the 0 that it did before when we did the homogeneous solution, and it has to generate this new particular solution. We already know our homogeneous solution was a sine of omega t plus phi, where that's our natural frequency from this term right here. We know that that's omega squared. And now we can look for the particular solution. And the particular solution needs to generate this function. So we'll assume that it takes on the form of our sine function over here, since we have to generate that. So x particular will be some b sine of beta t. Taking derivatives of that, we get b beta cosine of beta t, and x double dot as negative b beta squared sine of beta t. And now we can plug these terms into here to find out what our particular solution would need to be. And doing that, we'll get negative b beta squared sine of beta t plus k on m b sine of beta t will equal p on m sine of beta t. So we see here that the sine would have to have the same beta, that forcing frequency inside of it, and we can divide through by that, and that'll drop out. And from here we can factor out b, and we'll have k on m minus beta squared is equal to p on m, and recognize k on m to be omega squared. And that'll leave us with b is equal to p on m over omega squared minus beta squared. So that tells us this solution is valid, our xp is valid, if we use this as the amplitude. And note over here we have omega squared minus beta squared, and you should ask what happens as the driving frequency approaches the natural resonant frequency. As beta approaches omega, we have a division by 0, and we're going to find that b goes to infinity. And that's the case where we have a harmonic resonance inside the system, where we're matching up the driving frequency with the natural frequency of the system, and we can have amplitudes that will grow wildly out of control.
The actual collapse of the world's third largest suspension bridge. Give way and plunge into the water below. Fortunately, the only casualties were a car stalled on the bridge and a dog.
Putting all the pieces together, we got our final solution as x is equal to x max sine of omega t plus phi plus p over m over omega squared minus beta squared sine of beta t. And we can see here for beta equal to 0, it doesn't have any driving frequency. This term goes to 0 and we get our classic free vibration solution. If we look at this term alone, and again it's an amplitude, we have P on M, omega squared minus beta squared, and for beta going to 0, this term will disappear, and we get P over M omega squared, which will be P over M, and omega squared is K on M, which will give us P on K, which has units of distance, and this is called the zero frequency deflection. If we make a plot of this amplitude here, we can plot the value of the magnitude versus beta, and we'll find at 0 it starts out at our P on K, zero deflection, and as it approaches omega natural, we'll find that it asymptotically goes off to infinity and then returns and decays back down, eventually back to 0. So for beta approaching the natural frequency of the system, we can have a resonance problem here where there'll be a rapid growth in amplitude of the system, which could be quite destructive. Now in actual practice, all systems have some damping and some friction involved so that it can't really go to infinity, and this will generally be capped at some value, depending on how much damping the system has naturally. Examples where the forcing frequency approaching the natural resonant frequency of the system in engineering are abundant. Designing buildings to be earthquake resistant takes into account the length and mass of the building in terms of its natural resonant frequency, and attempts to avoid overlaps with the driving frequency of an earthquake. A long rod, like a building, has a natural K or stiffness to it, and omega is the square root of K on M. Vibrations in aircraft and high RPM applications are also a problem in engineering. The most effective way to control resonant patterns is to modify omega n or put in some type of a damping effect inside the system to help control these resonant frequencies. Let's next take a look at damping and its effect on a vibrating system. Here we have a simple vibrating system which we're modeling as a mass being driven by a spring, and we've added a dashpot to it. And a dashpot is a viscous damping device that removes energy from the system, eventually slowing it down and causing it to stop. A really good analogy for a dashpot would be a shock absorber, where we have a piston inside of an oil or a fluid, and the piston moves back and forth with some velocity v, and while it does so, the fluid is forced to go through a set of holes in the piston. We can adjust the size of the holes and the number of holes to get different viscous damping coefficients from this. And our equation will be that the damping force, Fd, is minus CV. It always acts opposite to the velocity because we have a buildup of pressure back here as it tries to squeeze past, and it's linearly related. As we increase the velocity, the damping force increases linearly with respect to that. So a shock absorber is a good model for viscous damping. As we develop our free body diagram, we have minus Kx, the spring force acting on here, and now we also have minus CV, our viscous damping force as well. And we can apply Newton's law. The sum of the forces in the x is max. Call that direction positive, and we'll get minus CV minus Kx is equal to max. And note here that ax is x double dot, and v would be x dot. So if we bring everything to the other side and write it as one equation, we get mx double dot plus cx dot plus kx is equal to 0, which we can recognize as a second order, linear, homogeneous, ordinary differential equation with constant coefficients. We know the solution will take on some form of x is equal to a e to the lambda t, where x dot will be a lambda e to the lambda t. X double dot will be a lambda squared e to the lambda t. And if we plug these terms all in, we get m a lambda squared e to the lambda t plus c a lambda e to the lambda t plus k a e to the lambda t has to equal 0. And we can see here that we can divide through by a e to the kt, and we'll be left with m lambda squared plus c lambda plus k is equal to 0, which is called the characteristic equation for the solution of this constant coefficient differential equation. And we solve this using the quadratic equation, where we're going to get a lambda 1 and a lambda 2. And that tells us then that our solution for x will be a e to the lambda 1t plus b e to the lambda 2t. So whatever we get from this quadratic equation becomes our coefficients on our exponential functions. And the process here for us is we recognize this equation and we go right to the solution set for the exponential constants right away. We don't bother going through all the steps to prove it every time. It's equivalent to knowing that 5 times 5 is 25 rather than writing it out as 5 plus 5 plus 5 plus 5 plus 5.
Huh? I'm surprised that you're learning. Now I'll show you. 5 times 14 is 25. 5 times 4 is 20. 5 times 1 is 5. 25. That's it.
In our case, we recognize this to have constant coefficients, and we go right to the solution set and then plug it in, and then we begin to chase down the constants. Now recall, we've been working with a lot of problems where we had no central term. And without a central term, this solution is still valid. Although you can solve for lambda immediately, we found that it was beneficial to use sine and cosine or sinh and cosh instead, depending on whether that was a plus or a minus inside of that function. And these were a little more friendly to work with for certain dynamic problems. However, an exponential solution would have also been valid. From here we'll get that lambda 1, 2 is negative c plus or minus the square root of c squared minus 4mk all divided by 2m, which you'll recall that this discriminant plays an important role in this type of solution set because our discriminant could be a real number, it could be 0, or it could be imaginary, based on the value of what's inside of here. When that is 0, we'll define that value of c to be c critical, and c critical squared will have to equal 4mk, which we can write as the square root of 4mk. And c critical is important. We use it a lot. It's called the critical damping coefficient, and it plays an important role in damped vibrations. From here, we can distribute the 2m as minus c over 2m plus or minus the square root of c squared on 4m squared minus 4mk on 4m squared. And the 4's will go here. One of these m's go, and we recognize that we have omega natural squared here as k on m. So the natural frequency of the system without the damper is making its way into our equation here. Looking over here, I see part of the critical damping function. So let's see if we can get that to appear. If we multiply and divide by a k, we see 4mk is c critical squared. So we'll end up with theta lambda 1, 2 minus c over 2m plus or minus the square root of c squared over c critical squared, and we'll have a k on m left from that, minus omega natural squared. And in the process of doing that, we've generated another k on m, which we know is omega squared as well. So we can factor the omega squared out in front here, and this cleans up to become, which is our generalized solution for lambda 1 and 2. And looking at that more closely, let's take a look at the three cases that we can have. Case A, C is equal to C critical. So this we would call critically damped. And such a system, we see that that goes to 0, and our solution then is x is equal to a e to the lambda t plus b t e to the lambda t. And there's only one lambda, we don't need 1 and 2. They're equal to a constant. In fact, if we check that constant, then we have minus c critical over 2m, because we're plugging in c critical here. The rest of it goes to 0. And c critical will be the negative square root of 4km. And let me bring this inside the radical by squaring it, so we'll get a 4m squared. And we see that the 4's go, one of the m's goes, and this becomes negative square root of k on m, which is negative omega natural. So we find that this becomes omega natural when we have the critical value. Some other interesting points about being critically damped. It represents the lowest possible value for C for the system to have non-oscillatory motion. And in general, the motion will pull it back to some amplitude A and release it, and it will decay down right back to equilibrium. It will represent the shortest amount of time possible for the system to return to equilibrium. So that's critically damped. Our next case will be that it's over-damped. Here we'll get two real solutions. So x will equal a e to the lambda 1t plus b e to the lambda 2t. And generally these will work out to be negatives. And if we plot that type of motion out, it'll look like this. It's so heavily damped that it actually stops and doesn't get a chance to return to equilibrium, And by far the most interesting and common case is C less than C critical, which is called underdamped. And for underdamped, we end up with an imaginary solution. And that's because inside of the radical, our discriminant, we get a negative number. And there is a way to solve that using an I value, where the solution from calculus is known to be x. It's a function of time. Will be x max e to the minus c over 2m. There's our initial value. Sine of omega d t plus phi. And omega d is our damped natural frequency. And we get our damped frequency from this radical up here, which modifies the natural frequency. And these have switched place because the process of bringing in an I here will reverse those. That's how we deal with that imaginary root that we have. And note that this will be subtractive, so omega d will be less than omega natural. And the effect on the period of the system, t is 2 pi on omega. As omega goes down, the period goes up. So it's going to slow the system down, and it will take longer to make an oscillation, which we'd expect. Since we have damping involved now, we wouldn't expect it to resonate with its original frequency. Now if we look up here, the E function here is decaying the amplitude of this, and that's what's happening in front. And then the natural frequency has been damped, so it's taking longer for it to make a period. So two things are happening. If we look at the motion, the amplitude itself due to the exponential function is going to decay like this. And then our period will take longer, so our oscillatory motion will look something like this as it decays out. So that term defines that range of amplitudes decaying per cycle. And also note that our period will have gone up when compared to the undamped vibrational system. Here we look at the case where we have forced vibrations with a damper installed as well. And our free body diagram would still look the same. We'd have minus kx, and we'd have minus cv. And our equation of motion would reduce to, and what we can see here, if we think of the plus 0 being over here, that we still have our x homogeneous solution for damping, and then we'll also have our x particular portion over there, and that will end up being x total. And if we put all the pieces together, we'll end up with this following relationship. So this is our homogeneous damped solution that we saw before, which has an exponentially decaying amplitude. And then this is our particular solution, which will be a response to the driving frequency beta that's acting on the system. And what's important to note here is that this term will decay away as a result of this exponential function decaying the amplitude. We call that a transient response. After which this will dominate and stay in effect, and we call that the steady state response. When we're looking at a damped forced vibration system, when it's initially turned on, both responses are active, and the motion can be fairly complex as it builds up speed. However, over time this one disappears, and generally in the long run we're worried about this term right here, and that's the one that we usually focus on. Now this value for x has gotten more complicated than when we last saw it, because we now have to include the effects of damping, where x max will now be p on m divided by omega squared minus beta squared plus 2 omega beta c over c critical squared to the 1/2 power. And note here that for c equal to 0, this term disappears and we get our undamped amplitude that we saw earlier, where if we add in damping, this additional term shows up. And this phase angle over here, phi, can be found by making a right triangle whose sides are omega squared minus beta squared and 2 omega beta c over c critical. And we find then that the tan of phi will be, and that's our phase angle. And the phase angle represents the difference between the applied force and the resulting steady state vibration. In general, X max is going to be the term that we want to find for the steady state amplitude effect on our system with the damping and a driving force included. We still see the traits that we've talked about. If the damping coefficient is 0, that disappears. And as beta closes in on omega, we have our amplitude going to infinity on us. However, we can see here with damping added to the system, this is going to increase the denominator. So as this disappears on us, our damping coefficient will allow this term to exist. It can reduce the effects of the harmonic resonance. And just so we have them all in one place, recall that omega natural is the square root of k on m. C critical is the square root of 4km. And generally when we're working with these problems, we want to solve these beforehand based on the original information. If we have a rotating imbalance that's causing the forced vibration, we can find the magnitude of P max as ma sub c. It's the centripetal acceleration of that little rotating mass. So the mass is spinning around with some beta, and it's going to have a little a sub c in here, and that will be mr beta squared, which is an r omega squared type. And that's how we would find this value here for P max inside of that equation. It's also possible to have a displacement oscillation which can excite a system. And for displacement oscillation, we'll vibrate the mount that holds the spring without having a forcing function on the other side. And this will act as a forcing function as well. And the way we address that is we have some deflection max that this imparts to the system. And then the spring force, when we calculate it, become minus kx plus delta, where we have some delta in here that's oscillating the system. And delta will be delta max sine of beta t. And if we drag that through, we'll get the same basic solution set. And that deflection can be converted into an effective force. So P max will be K deflection max for the system. And that value can then be placed into here, that either P will work. If we have a rotating imbalance, we'll use this to calculate P max. If we have a displacement excitation, we'll use this term to calculate P. And then we're back here trying to solve for the maximum amplitude of the system. Let's take a look at a problem that involves these terms. Here we have a rotating motor that sits on 4 springs. The motor has a combined mass of 50 kilograms. And there's a rotary imbalance inside of here. And it's effectively 2 kilograms of mass with a radius of 50 millimeters, and it's spinning at a rate of 10 radians per second. And we're asked to compute the maximum amplitude of the vibrations while this motor is running. So to do that, we'll start by computing some of our background information. K total here will be 4 times 1800, and that'll be 7200 then. we should find omega natural of the system. Square root of k on m, which will be the square root of 7,200. The mass of the system is 50. And that'll give us 12 radians per second for our natural frequency. We should calculate C critical just so we have it. It's the square root of 4 km, which will be 4 times 7,200 times 50. And that will give us a critical C of 1200 Newton seconds per meter. And again, this is just data that we can have. Over here from the imbalance, we can calculate the value for P. So P max will be ma sub c. So this little mass has a tiny a sub c. And as it rotates, the a sub c points in different directions. And we know that that'll be m r beta squared. The small rotating mass is 2 kilograms. The radius is 0.05 meters. And we're spinning at 10 radians per second squared. That's 100 times 2. We're going to get 10 newtons from that. So P then will be 10 sine of 10t. And that's our driving force, and there's our maximum P, and there's our beta inside this system. And with that, we have all of our background information, which I'll write over here to keep track of it. And let's look at the case where it's completely undamped. What will the vibrational amplitude be? And we know when C is 0 over here, this whole term drops out, and we're left with just our undamped amplitude. So the undamped amplitude will be P over m, omega squared minus beta squared. P is 10 newtons divided by 50 kilograms over 12 squared minus 10 squared, which will be 144 minus 100. So we'll get 10 over 50 divided by 44, which if we manipulate the units, this is also negative, by the way. We'll get negative 4.55 millimeters for that. So without damping, that would represent the amount of vibration that we'd expect to see as this thing was running. Now let's add in some damping. Let's have C be 600 Newton seconds per meter, which gives us a C on C critical of 1/2. And we can see over here that the natural frequency and the driving frequency are very close to each other. So there is some resonant issues developing here. So for the damping factor, then we have to do the full equation. So X, case B, this is case A, will be 10 over 50. And we have the same omega squared minus beta squared plus 2 omega beta over C critical squared to the 1/2 power, which will be 10 over 50. We already saw that that's going to be 44 squared plus 2 times 12 times 10 times 1/2 squared for 1/2 power. We look in here, these 2's cancel out, and we have 120 squared here. So we have 44 squared plus 120 squared, then square root of, and that'll end up being 10 divided by 50 over 127.8. And we can see how much the damping has helped from the 44 that we had before, and that will give us 1.56 millimeters. So we have reduced the amplitude to more than half of what it was originally. Now we could also look at extreme damping, case C, where C is almost C critical, so we get a C on C critical of 1, just to see what happens here. So in that case, this would still be 44 squared. And here, rather than 120 like we had here, it would be 240 squared. So if we had an extremely powerful damper in the system, and we'd end up with an XC of 10 over 50 divided by 244 now, 0.82 millimeters. So that would be extreme damping, just to see what that number would end up looking like. Here's a magnification plot that summarizes our findings. On the x-axis, we're plotting the natural frequency, and ours is 12. The red vertical line is the beta of 10, and you can see the different damping coefficients that we used, a C of 0, 1/2, and a 1. And it should be clear that our beta is in the harmonic resonance regime, and without some damping, the amplitude could become quite large. Now, if none of these solutions were adequate, what else do you think we could do to reduce the steady state amplitude for this system? Well, one thing would be to look at this beta, the rate that the motor is running. We want this to rotate faster, turn up the value for beta, or lower it. And we would want to lower it because we want the difference between these two to be as big as possible. So if we were able to run this at, let's say, 8 radians per second, we'd see a very large drop in the amplitude. Just doing that would make the undamped value 2.5 millimeters. What if the new guy comes and said, let's add weight to this? Let's just put some mass on here, and that ought to slow the system down and improve these vibrations. Is that a good idea or a bad idea? Yes, good idea, or no, bad idea? Well, if we add weight to the system, that's going to change the natural driving frequency, and omega natural is the square root of k on m. So as m goes up, omega natural will go down. And omega natural is at 12, and we certainly don't want to bring it down any closer to the 10. In fact, if they put the wrong weight on there and they get this too close to the 10, this whole system will fly apart and break the springs, and you could cause some serious damage. So the answer here is heck no, don't do that. Fire the new guy. Or send him for some training. In fact, if we look at this equation, we'd ideally like omega to increase. So we could do that by increasing k or decreasing m. And looking at this motor, I don't think we could decrease the weight of it easily. However, if we had to, we could replace the springs. Let's say we go out and we get springs that have 2,500 newtons per meter times 4. So now we'd have a 10,000 newtons per meter. That would give us a new omega of 14.14 radians per second, and that would translate out into a maximum deflection with no damping of 2 millimeters. So stronger springs could reduce it. And then if we do get a viscous damper, we can cut that down further, so we could get that probably below 1 millimeter. So there's a host of things that you could do as an engineer where you have some control over the natural frequency of the system. We could ask if they could run this at a lower RPM. We could add viscous dampers to it, or we could also come in here and try to balance this thing a little bit and fix the motor. So there's a family of choices that we could have. Here's some examples of these oscillators. This one's a undamped system oscillating for 14 seconds. Here's one that is underdamped for 14 seconds, and notice how it's decaying down exponentially. This one's critically damped, and it has the fastest time to stop, a little over 2 seconds. And this one's overdamped. It stopped, but notice how it took a little over 4 seconds for that to happen. Thanks for watching.